Okay, good morning. Let's have a class. And we have a lot going to talk today. And we're going to finish some of the section here, then move on to the slides 2. So, electron carrier we mentioned about, which is an NAD, nickel-adenine adenine dinucleotides, nickel-adenine adenine dinucleotide phosphates, following adenine dinucleotides. And this is a very good table for all these conclusions. And you can see what that happens. You also going to be noticed here, I want to let you know that what it means by reduce. Reduce, we mentioned they're going to have an electron, is that right? But at the same time, if the chemical receive proton, this is also another way to talk about reduce. So let's say you have an NAD. You have 2 protons, then you have 2 electrons, then you become NADH2. This is also called reduced. Not only for the electron, if you have a proton there, and when you see here NAD plus, you can think about there is 2 empty boxes there, which is called fit H there. Okay, then become NADH2. And I want to also mention all these electron carriers. The very important for bacteria to survive, they has to be recycled. Especially during the life cycle, they need to have these free available like this. We will give you an example, talk about fermentation and glycolysis to explain to you what this means. But I just want to make sure here. Okay. Here, I would love to say NAD, FAD, but also using in catabolism process. NADP, which is for the anabolism process, which means the biosynthesis. Okay, so that's the electron carrier. Chemosmosis we already mentioned. Peter Mitchell in 1923 mentioned about this theory, win the Nobel Prize later to talk about the ATP generated going through electron transport chain. So we'll just briefly mention here because we already talked about the details. Okay, metabolic pathway. Metabolic pathway, it's relatively, say, there's a different morphology, we can say. It could be a linear. So what's the example? Fermentation. The reaction is linear. It could be kind of like a branch. This we will talk real quick. Let's say glycolysis. And most of the time you see it's like a circle. What's that? PCA cycle. So these 3 are very typical morphology. I just call quotation mark morphology for the metabolic pathway, what they're going to happen. Now, we want all of the metabolic reaction happen efficiently, which means as soon as possible. Therefore, we need some other things to help. That is enzyme. So what is enzyme? We want to spend a little bit of time talking. So first of all, what is enzyme? Bacteria has a substrate. Usually in their living environments, it could be glucose, sucrose, carbohydrates. Then they will generate a product. And their products, most of the time we talk about in the lab, it's a gas or acid or alkaline, all those stuff. They want to let the reaction happen quickly and more efficiently than they want an enzyme. So what's the function of the enzyme? If we want to draw a picture which looks like this, the x-axis is a progress of reaction. And the y-axis, if you look at the picture there, that is delta G 0 prime. Now, I also want to delta G 0 prime, which is set up at pH 7. So this is one is typically for biochemical reaction, specific for biochemical reaction. And you see sometimes delta G. This is for physics person. So that's a little bit different. That's why on the textbook you see is delta G 0 prime. That's a free energy. So what's the function of the enzyme? When you have something happens, like this. Here, you see a little bit of curve right in the middle. This is activation energy. What is that? How to understand? We're going to go back to this ball question. We had a ball right here. And we say this is a big H. And we go here, we have this small h. Then the ball goes to here. They fall down. Spontaneous reaction happened because delta H is decreased. However, I said it's not going to happen naturally. You're going to have to push it. What this push means, it is activation energy. And what's the function of the enzyme? If you do not use enzyme, they need lots of activation energy. If you use an enzyme, this activation energy will be much less. So that will be the curve if you use enzyme. Okay? Now, we want to mention about the enzyme. Enzyme, most of the time, it's a protein. However, it does not mean all the components is a protein. So if you look at the slides, this tells you very detailed. Most of the enzyme used in a biochemical reaction for bacteria is a hollow enzyme. The hollow enzyme has two different parts. There is a major part, which is protein. We call it apple enzyme. And another part, which is non-protein part, we call it cofactor. And this cofactor could be separated into two categories. If it is loosely attached, we call it coenzyme. And I tell you, most of the time, the coenzyme is a vitamin. It's different type of the vitamin. And there is also closely attached part. That is called parasitic group. And this we don't mention too much here. Okay, lots of the time we are interested about this vitamin, which is a coenzyme. So, especially when we later on talk about RNA polymers, we will talk about this later on, more detail. Okay, the next week. So that's a protein part of the enzyme. It's an apple enzyme, the halo enzyme. Now, when we talk about this enzyme, we also want to mention about is the relationship between the substrate and the enzyme. So we often think about, you're going to add enzyme. We're going to let it happen more quickly. Okay, keep doing. Does not mean it's linear. Which means it's not going to happen is you add more enzyme. Okay, it's going to, the reaction happens more quickly. Still use a figure to do the expression. You look at the slides. This will be the substrate concentration, which is x-axis. So So S. And this y-axis, if you look at the picture there, which is speed, and we call it velocity, is actually the speed. So, non-linear, what happened? Kind of like a partial of your bacterial growth curve. And later on, it will become saturated. Then we'll reach a V maximum speed. So at the end of the day, the enzyme will be saturated. So the speed will be reached a maximum. Now we are more importantly, more interested in think about is something right in the middle. This comes out with a very important concept in the enzyme science area called Michaelis constant, which is Km. What is the Km means is right here. That is the substrate concentration required by enzyme to operate at half of its maximum speed or maximum velocity. And we know that there is a formula talk about is V equals V max multiplied by the substrate concentration Km add concentration of the substrate. And this is interesting. Later on, it will become a curve between speed and the Km reciprocal number. Okay? Now, you're going to be learning about in the biochemistry a lot, talk about that. And it's difficult. Why? Because it's not a linear. It's a relationship equation. Okay, so, but we just barely mention about here, so it's not a biochemistry class. But just want to let you know about they using Michaelis constant Km value to talk about the relationship between substrate concentration and the velocity of the enzyme. Velocity of the enzyme reaction. Now, some things are common sense you need to know. Because enzyme is a protein, the major part of it is a protein. Therefore, it is heat sensitive. Because protein doesn't like heat. Once you heat it, it's going to melt it or degrade, whatever you call it, lose the function. Because it is a protein. So, the fact to affect an enzyme, it's very simple. Number one is pH. So when you look at the curve here, for most of the bacteria, the optimal pH is 7.0. The second thing is temperature. Most of the bacteria is mesophile, so that's temperature, 37 degrees Celsius, and this is 7. That's why most of the bacteria we grow, we put in the incubation at 35 degrees Celsius to let them grow dramatically, because that's a temperature their enzyme could have a biochemical reaction more efficiently. Now, of course, it's related to the substrate concentration, the final product, and the enzyme concentration by itself. So that's a condition that will affect the enzyme. Now, how to regulate the enzyme? We want to talk about two examples. You read already, so I'll just be briefly. Number one, we call it a competitive inhibition. Competitive inhibition is related to a very important chemical, which is very interesting. This chemical is called PAH. BA, beta benzonate. This is a chemical, is a precursor for folic acids. And the folic acid has to be synthesized when the bacteria taking the material outside of their body cannot synthesize by itself. So they need a PABA. And sometimes I want to cure bacteria. So I will use antibiotics. We already mentioned the penicillin, ampicillin, amoxicillin, all those things. If there is antibiotic resistance happens, I cannot keep using those antibiotics. I need to find another way to do, which is prevent the metabolic pathway. So what I'm using? Using a called sulfur drug. Sulfur laminate, which is an example. And the morphology of the sulfur laminate looks very similar to the PABA. What it looks like, if you want to draw, it looks very similar. It's S, then NH2. Let me double check. Yes, exactly the same. Only part, this is the carboxylic acid. This is a sulfide double ketone. You can understand about that. Have amino group. Therefore, once you have this guy right here, let's say, okay, I have this enzyme. The PABA originally should go there. Is that right? I don't let PABA go because my morphology is very similar to that. So I'm going to go there. Therefore, I block the enzyme to react with PABA to synthesize folic acids. Because folic acid is essential for the bacteria to grow. If you don't have folic acid to formed, the bacteria will be died. But most of the time, you know it's not died. It is actually inhibition. Okay? So that's some of the story called the competitive inhibition. We have competitive inhibition. Then we have another one called incompetitive, non-competitive inhibition. That is usually, right here. Non-competitive inhibition basically is using heavy metal, like mercury. Okay? So this is one of the ways to adjust the enzyme function. Another way what we could do is allosteric reaction. So instead of I'm going to react with the substrate of the enzyme to have a competitive, non-competitive reaction, what I'm going to do, let's say I have this guy here. Okay, I'm going to react it with something. Let's say, okay, I have an enzyme, I have a substance. I'm going to do something on the side. I'm going to attack here. So some chemical going to attach here. Attachment, I will just say. So this morphology is going to change. It's not going to be like this. It maybe becomes like that. Then the substrate and the enzyme cannot attach, cannot be reacted. And this is called allosteric reaction. And which one is a good example of this is what we're going to talk next week, lacto-operon. Lacto-operon, if you learn in your genetics class, it is actually a good example for allosteric reaction. Okay? Last one, we also need to talk about is called feedback inhibition. feedback inhibition. A very simple example, you know that. If you eat too much, you don't want to eat more. So, A, go to B, go to C, go to D. If this D is too much, they will go back to tell A, please do not generate. They could be go back to tell B, please do not generate, or maybe just tell C, do not generate anymore. That's called feedback inhibition. It is quite common in the bacteria because in the very short lifetime, they have to be economically using all the energy. So feedback inhibition actually happens a lot. The end product concentration could be reacted to the intersection chemical, or they could be directly go to the top. Look like here is a substrate A. Okay? So we were very quick to talk about the enzyme because we already learned in the other classes. I believe you already learned. So we'll skip these relatively quick. Then we're going to move on to a big class today. We are going to talk about some biochemistry stuff. Okay. So this is what we have, and then we have to take all these out. Take all these out, and then second section of the class will be talk about three major biochemical reactions. Is fermentation, glycolysis, and citric acid cycle. Pentose phosphate will be briefly mentioned. The key thing here is the characterizing ATPs. So we will talk about that later on. First slides, we are just using the slides to talk. This is categorized microorganisms based on their nutrition resource, based on their carbon, energy, and electron resource. So if their carbon coming from, you can say coming from sunlight or coming from carbon dioxide, that is autotrophs. If their carbon resource coming from organic molecules, we call it heterotrophs. The second category is the energy source. If they coming from light, let's say cyanobacteria, we just mentioned on Tuesday, that's a phototrophs. If the energy resource coming from organic, inorganic compounds, it's chemotrophs. The last one is the electron sources. If they are coming from reduced inorganic molecule, we call it lysotrophs. If it's coming from organic molecule, we call it organotrophs. Now, the difficult thing here is most of the time, a bacteria is not only belonging to one category, it is belonging to a bunch of them. Then we have to put them together. So this is confusing. You look at it here. For example, we mentioned cyanobacteria. That's photolysoautotrophs because the carbon source is carbon dioxide, energy source is light, and the electron source is inorganic electron donor. Then we have a photoorganoheterotrophs, chemolysoautotrophs, chemolysoheterotrophs. But what we are interested in this class, we talk about E. coli, Salmonella, Listeria. They are not belonging to above 4 categories. They are belonging to the last one, which is chemoorganoheterotrophs. Their carbon source is organic carbon, possibly glucose. Their energy source is organic chemicals also, possibly glucose. And their electron source is organic electron donor. Therefore, right here you will see most of the bacteria, most non-photosynthetic microbes is belonging to this category. So what we learned in this class and also in the lab so far, they belong into chemoorganoheterotrophs. That's the reason why we want to talk about all these cycles. Okay, so this is the outline. We want to talk about aerobic respiration, anaerobic respiration, and the fermentation. Now, before we go all the detail, we need love to introduce you with a concept which is using electron transport to talk about this concept. So how you explain here? This is going to be talking about the electron transfer concept. So, to explain. So first of all, if electron donor is organic chemical, and the electron acceptor is also organic chemical, this process is called fermentation. And I also want to tell you, this is the best definition to explain fermentation. Second, if electron donor is organic chemical, and electron acceptor is inorganic chemical, this is called respiration. And the respiration, based on this inorganic chemical, we separate them into two categories. If this inorganic chemical is oxygen, we call it aerobic respiration. If this inorganic chemical is others, or we say other than oxygen, let's say sulfide, this is we call anaerobic respiration. This is what it belongs to. Okay? This is a little bit different from what you learned in your other classes. Here we want to introduce this concept before we go everything detail. So let's repeat it one more time. If electron donor is an organic chemical, electron acceptor is also an organic chemical. This is a fermentation. And I will give you an example real quick. If the electron donor is organic chemical and the electron acceptor